focus here. It's my pleasure to introduce everybody to the first ever, for my group at least, Zoom PhD defense. I happen to be with the person who deals with cameras, Melvin. That's so, maybe it's for a good cause. Melvin has been in our group for the past 4 years and 2 months and some days, to be exact. He got his master's from Drexel before that in 2014. And before that, he got his bachelor's from India in mechanical engineering from Calicut in the National Institute of Technology. So Melvin's PhD thesis has been focusing entirely on optical metrology, which is the topic of his defense. Melvin, you have the process in front of you. You have the public defense where everybody's going to be here listening to you. You have about 45 to 50 minutes to wrap it up. We're going to accept some questions from the audience, then the general audience will step outside the Zoom meeting. The committee will stay. We're going to have a session with you, and then you will step out. We'll discuss, call you in, and announce the result. Sounds clear and fair?
Yep.
Okay. I think Professor Chang is here. And since Professor Chang is here, I forgot to acknowledge.
Oh, okay, just done.
Yep.
Dr. Chang.
Forgot to acknowledge the members of the committee. The chair of the committee is Professor B.C. Chang from the Mechanical Engineering Department. Also from the Mechanical Engineering Department, we have Professor Mark McCarthy and Professor Alan Lau. And from the Department of Civil Architecture and Environmental Engineering, we have Professor Ivan Bartoli, who also served in advising Melvin for a big portion of this project. So Ivan, thank you for being here. Everybody, thank you for being here. And Melvin, whenever you're ready, you can start your defense presentation.
Sure, perfect. As Dr. Kamsa said, I want to thank everybody for being over here. My name again is Melvin Mathew, and my thesis is titled Speckle Patterns for Tailorable and Multiscale Optical Metrology Measurements. I've been working in this field of research for about almost 4.5 months under the advisorship of Dr. Antonius Consos with the Theoretical and Applied Mechanics group at Drexel. So first, I'm going to start off by explaining sort of like an overview of everything that I'm trying to achieve with my slide. And then I'll break down into the simplifications and actually talk you through the outline as well. So with my thesis, what I'm trying to do is essentially extract multi-scale quantified measurements for measuring motion, deformation, and damage by using photogrammetric methods. Now, the photogrammetric method of choice is digital image correlation, which helps me identify these surface deformations. My goals then are to develop optimized scale controlled deformation trackable patterns, develop pattern overlay techniques and extract this multi-scale deformation information from a structure or a specimen, anything that I'm testing, and finally use this full field displacement data to enable model updating towards a digital twin approach. And I'm going to break down into the details of all of this within the next few slides. So this is my outline. I'm going to walk you through the motivations. I'm going to start all the way from the beginning with the motivation, identify the gaps and challenges, the objective and hypothesis that we created, the approach, state of the art, finally my results and the conclusion. With the motivation, as I said, I am going to start at the very beginning. So the first recorded history of metrology was the use of the cubit stick, which is basically the length of the pharaoh's arm all the way from the base of his elbow to the tip of his middle finger. And this standardized unit of measurement helped the Egyptians build all these amazing, wonderful structures across the world. I mean, in Egypt. Sorry. But from then, within our modern system itself, the metric system, as part of the AI kicked in, as part of SI kicked in, which we have to thank the French Independent Revolution for in 1795, where they declared 1 meter was 1/10 millionth of the distance from the pole to the equator. And as such, to standardize this length within traders, there have been established little structures such as this around the city and eventually around the countries where they shared the same commonality. In essence, then, metrology is the scientific study of measurement. Within the field of optical metrology, the first recorded history of optical metrology was a scientist named Francois Arago, who used camera systems as well as triangulation to be able to assess topographic data. Now, with the advancement of technology, we use optical metrology even in space to help astronomers unlock the mysteries of the world by using lights or the lack of lights within the stars. Moving on with that, the advent and extreme use of computer vision in optical metrology is primarily because of the access to cheaper imaging equipment and faster computational hardware. Optical metrology allows us to do things such as matching and sorting, object recognition and tracking, and moreover, it is very fast and very reliable, as you can see with this tomato sorting machine. Within the field of mechanical engineering, however, if my button has been clicked, yep, we can use optical metrology for crack detection. And this over here is part of a MATLAB code that we wrote that can assess the length of a crack at 0.56 meters. We can also use this on remote sensing by just attaching cameras onto UAVs, where we can measure damage growth. We can measure surface artifacts of defects. We can even measure subsurface artifacts by using innovative optical metrology tools such as infrared cameras, where we can detect the laminations. Using that as my segue into damage, we all know that damage is a cumulative process. Damage is going to start small within the microscale. It is going to grow larger with continued loading or with fatigue or over time or with corrosion, where this damage is going to be excessive to the point of catastrophic failure, such as a bridge. Within these structures, such as bridges itself as well, there are routine inspections that are being carried on. And these routine inspections within the state of the art right now is having visual inspectors physically go to the bridge and check it out. However, with that, the drawback is they could overlook the slow global degradation. They require expensive equipment. They need a large number of trained personnel to continuously evaluate and maintain these 617,000 bridges across the US. The quality of the inspection then obviously relies on the expertise and experience of the inspector, and accessibility around the entire structure could prove tough. However, even if the inspectors do notice a little bit of amount of damage, by somehow getting access to the structure all around it, you could still miss out damage, which could eventually cause catastrophic failure. Now, to measure catastrophic failure, we can use static or dynamic measurements, right? So we could use simple techniques such as, let's measure what the position is. Let's measure what the velocity is, find out what the acceleration is, or we can just even identify strain localization by using strain gauges or the FPGA technology. The caveat, however, with these techniques is that they are very scale dependent, which means this strain gauge that I'm using over here is only going to give me the value of the strain directly underneath it and cannot be used for for another region of interest. Same with the laser displacement sensors. There's a certain range within which it works, as well as with sonars, taking that as an example for topographic mapping, there's a certain range within which this works. The problem then is that if I'm looking at a system from too far away, I'm going to miss out this micro scale growth that is going to cumulatively grow into this catastrophic failure, right? However, if I'm looking at it from too close by, I'm going to miss out this slow global degradation, which could then eventually miss out into catastrophic failure. And further, these contact sensing methods are also strenuous to connect. They require power, they're very labor intensive. And just as an example, let me say, let's take a wind turbine blade, right? Now, wind turbine blade is subject to different wind conditions. I want to know how this blade is going to act under loading. I'm going to attach a displacement sensor to the middle of it and identify how it moves. However, that is still giving me information of just one singular point. If I want to know how the entire blade is going to move, I'm going to have to attach multiple sensors across it. And now this is giving me information across the entire blade. However, this is still in one dimension. If I want motion in all three dimensions, I'm going to attach so many more sensors where now it is not only just a wiring nightmare to extend this to 3D. The question is, are we truly now studying the behavior of the blade, or are we studying this composite structure that we've created with these contact-based sensors and now the blade, right? Further, going on with the wind turbine itself, a structure such as that is subject to non-linear loading conditions with wind that could be subject to all the way from just regular gusts of wind to storms. And we need to assess the reliability and the longevity of these parts. The best way to do that is to simulate these expensive components, which obviously in real life we can't push to damage every time we want to assess. We can simulate these component behaviors under various conditions. However, the simulations are always going to be pristine. So, but to make sure that simulations reflect what's happening in real life, we're going to have to take this data from real life and make the simulation match it. So if we want the entire simulation to match what's happening with the system, we should ideally be getting three-dimensional non-contact data. Therein enters my use of digital image correlation, where we are going to use, where DIC is a non-contact method to view three-dimensional displacements in full field. Over here, you're seeing examples of a dummy crash test. We're seeing an example of a rubber bullet being shot at a helmet and of a bulb being broken. And this is what the use of DIC is. I can use a camera system by stepping away from the structure and still extract this full field three-dimensional data. Essentially, how DIC works is by breaking this image from the undeformed condition, saying there is no damage, and then take images as it damages. The system then breaks down the image into these little square subsets, and I'm going to explain a little more detail about subsets, and it's going to track the features within that as it deforms. And it's going to do this for the entire field of view and then subsequently get me the full field displacement. How I explain it when I teach the MEM 331 class or when I do the non-destructive evaluation DIC lecture is, say I take a t-shirt in front of you, right? Say it's a Drexel t-shirt, I'm holding it in front of you, and then I stretch it. And now you know that I've stretched it because you see it deform. You see it deform because now you're identifying these little features within the shirt itself that are stretching. However, if I showed you just a simple part of the shirt with no features at all, you would not know if I just moved the shirt to the left, to the top, if I did stretch it, or if I crumpled it up, because there are no features to help you identify this motion. And this, in essence, is what DIC does. DIC is a photogrammetric matching and tracking algorithm, which also means, given these features that we're seeing, that the pixel resolution between the features limit what the amount of displacement information we can get from DIC is. And again, because this is a camera-based system and it's scale invariant, I can use a camera to image a small specimen or a large bridge. And that scale invariance, that versatility that DIC brings, is why it is being used quite a bit, especially in the field of experimental mechanics. As you can see, the algorithm that we're using with DIC can measure the same 60 millimeter wide specimen as well as 250 micrometer wide specimen with the same algorithm to get us full field three-dimensional data with not contacting the specimen itself. Because we are now tracking the features within the image, there are certain rules for the speckle pattern application. Similar to attaching multiple sensors on that wind turbine blade, we want to make sure the speckles that we're applying does not affect the properties of the specimen. It should be reliable, it should be repeatable, and it should be reproducible. As such, there are various applications for applying speckles on different scales. 90 to 95% within the meso scale, which is about centimeters to maybe a meter, is by the use of just a simple can of black spray paint over white paint. Depending on the scale, we can use toners or lithography. There's also recorded literature of people using simple permanent marker stencils and hand applying these speckles. There are cases of stencils being used for larger surfaces, paint guns, and even naturally occurring patterns can be used as speckles to track the features as they move. Outside of the optical spectrum as well, DIC and the tracking of these features as a system deforms has been used even in the UV spectrum by using high temperature resistant paint as the structure deforms. However, the fundamentals is that the quality of the speckling, the way that we apply it, depends on the experience and skill of the user. And we have established that the quality of the speckling then relates to the quality of displacement resolution I can extract from DIC. This brings me into my gaps and challenges. So first of all is the non-repeatability of speckle patterns. And as Dr. Wisner, who was the power user of DIC in our group, had me do, I was applying copper nanoparticles on a small aluminum specimen to image under a scanning electron microscope or an SEM. So this is done by air compressing copper nanoparticles through multiple layers of filters to get the finest, smallest particles of copper on my specimen. And I applied it. It looks pretty decent, except I'm missing out enough features within these spaces. So I say, what the heck, I'm going to apply it again. I've completely ruined my field of view because that top right corner that you're seeing is completely saturated and I cannot get any displacement information from that region. Now, while the speckle patterning technique did not affect the properties of the specimen, it was, however, not reliable, not repeatable, not reproducible, and took another 4 hours of my life just to go back, clean it, repolish the specimen, and bring it back. Which means that this speckle pattern application depends more on user experience. It is more art than it is science. Secondly is the non-parameterized application of speckle patterns, which means this random application of speckle patterns that's in literature and is conventionally being used are not based on the theoretical derivations intended to reduce errors. Finally, this is an example with Correlated Solutions. It's a company that creates a commercial DIC software where they're showing 2 static images with differently sized speckles, where you can see the increased amount of noise for the speckles not being of the right size. And therefore, that actually affects the quality of the results that you can get. Thirdly is the scale transition. I want to be able to see local damage as well as identify global damage. And with DIC, say I'm looking at this region of interest where I have these features, which are these black dots, my DIC algorithm is going to break the entire image into these little square subsets that it's going to track. But say I identify a crack somewhere nearby and I go slightly more closer and I want to evaluate with DIC, I can't do that because now my speckles are way too large and it's going to saturate my field of view where I can't understand what's happening underneath. If I could, I get data points across this entire field of view, which I could use to assess the structure. With those data points, I could then take that and apply that or use that within a finite element model to train my finite element model to replicate the behavior of my actual system, and then I can push my system to failure. Over here, we see one of the examples from NASA where they actually did a crash test of an aircraft by using DIC to extract the features as opposed to what the simulation says the crash model is. With these gaps and challenges, we then identify the objectives and my hypothesis. The fundamental hypothesis that I'm making in this dissertation is that naturally appearing patterns analyzed with digital image post-processing methods could reveal metrics that could help in designing and tailoring speckle patterns that will improve the quality of displacement resolution computed with the use of digital image correlation. Essentially, when I'm breaking that into objectives, I believe that I can improve the displacement resolution by optimizing the patterns being matched and tracked with the DIC. And for this, I'm going to leverage these optimal patterns by understanding what the quality metrics of them are. Once I have that, I am going to try and overlay these patterns where a pattern that's giving me the damage at one scale, say the global scale, is not going to interfere with the results of the pattern of the other scale. And I assume I might be able to use these separate bands of electromagnetic spectrum, which was similar with the high temperature testing. Further, I believe using that technique, I can then detect damage on different scales by using DIC within the same region of interest, by generating these size controlled speckle patterns, and then finally create full field, take this full field experimental data and extrapolate and use that within a finite element model to update the model to understand what the behavior is under different loading conditions. With that, I'm going to walk you guys through my approach. First, I'm going to run testing at different scales. And for this, I do testing at the macro scale, the meso scale, the micro scale. And I want to say about in my 4 years at Drexel, I've probably done around 1,000, if not slightly more, DIC tests, right? The reason I'm doing this is because I want to know what the user hardship, I want to learn that lesson of what the user experiences right now, the conventional best state of the art, with applying speckles at those scales, extract those speckle patterns, validate their quality metrics, identify what makes a good speckle, and then take that good speckle for a pattern analysis, which I'm going to do within the frequency domain. Now, I'm going to run some numerical testing error analysis, and using all of this information that I'm learning, I'm going to create my optimized pattern. And then from there, I'm going to take all of this out of the computer and actually test this physically to see if what I believe is my theoretical optimal pattern, does that actually really work within the DIC environment? And finally, I'm going to use that for multi-scale, multispectral testing, and then move into extracting this full field real experimental data within a model updating parameter. In essence, my approach is going to be broken into 4 different regimes. First is identification analysis. Second is optimization creation. Third is testing and validation. And finally, it's applications. So walking into the state of the art, as I said, DIC is basically a matching and tracking algorithm, right? What is going to be matching are these little square boxes, which are known as subsets, where it's going to track the features underneath it as it deforms from the reference image all the way through the deformation images, which means the fundamental assumption in DIC is this neighborhood of points that's in my subset is going to remain as a neighborhood of points as it deforms as well, right? Now for that, we need to understand practically the limitations, which means there are lighting limitations. When I'm applying light, I want to make sure I have diffusive light or not specular. And what that basically means is I don't want glare shining into my image, which is just going to give me a big white spot from which I have no features so I can track. So there always has to be diffusive lighting. Further, these features have to be confidently registered within the imaging space itself, which means each of these speckles should have at least 3 by 3 to 5 by 5 pixels within the camera sensor. And each of the subset, remember that neighborhood of pixels that the subset is following has to remain as the neighborhood of pixels. So that uniqueness has to be there while it's searching for it, which means each of these subsets has to contain at least 3 to 5 speckles, which are sized between 3 to 5 pixels each. As such, there are fundamental rules towards the speckle pattern development. Uniqueness is key. For that, we need the speckle patterns to be non-repetitive, it needs to be isotropic, and it needs to be high contrast, right? So moving into how subset tracking is, say I have this image, I know my requirement for minimum subset size. I'm going to select a subset size of 20 pixels by 20 pixels. And this bar plot over here is what the algorithm is seeing. It is looking at the dark spots and saying, hey, that's close to 0. It's looking at the white spots and saying, hey, that's close to 1, right? But once this subset starts deforming, what the algorithm does is create a search window. It's going to search for this grayscale, this bar plot within that search window, and use a cross-correlation algorithm to identify which part has the closest similarity and pick that point, which means each one of these subset centers is then a data point that gives me displacement for that part of the image. And this size of the subset is determining how much amount of the grayscale value is contained within that neighborhood, which means increasing my subset definitely increases my confidence in subset tracking because there's a lot more information within it. It increases my quality of my quality metrics, which obviously is validated by the increased confidence in subset tracking. It reduces my random bias error. It however lowers my spatial resolution. There's been reported cases of problems matching sharp corners, and the computation time significantly increases, right? So now, knowing how subset centers work, there is another use of control known as step size. This basically determines how close is one subset center from the next subset center. And that is determined by the step size, which means over here, say I have a subset of 20 pixels by 20 pixels, and my step size is another 20 pixels. That is 0% overlap. In literature, however, they recommend that we have about 45 to 55% overlap, which means we have a lot more number of points. Therefore, by reducing your step size, you're increasing the number of points that you have. However, you also do increase the computation time, and you also subsequently increase the noise within your strain function. Now, in the back end of the DIC algorithm, we obviously understand that, hey, deformation is not going to be a square moving left slightly. Deformation could be in different complex shapes. As such, there are shape functions written into it. Using that same line of thought, we also realize deformation is not going to go from 0 to 5 pixels to 1 to 6 pixels. There could be sub-pixel deformation. And for that, interpolation functions are used, which changes those bar plot grayscale values that you saw into more of a surface, which can then be tracked to extract sub-pixel interpolation values. And then with DIC, there is also an error analysis. Now, these are the equations for the biased error and the standard deviation. What I want to bring your eyes to over here are the denominator functions. And these are essentially just image gradient values across the entire field of view within that subset. What this tells me then is, hey, if I increase that denominator, if I increase my image gradient value, I'm going to subsequently end up reducing my error. And this could be a theoretical formulation that I could use to improve my spectral pattern qualities. Now, this lower function over here is known as the sum of square of subset intensity gradients. And this could then be a local quality metric, which means without even conducting a DIC experiment, by just imaging what the speckle pattern is beforehand, I know what to expect from the quality of the results that I'm getting once I do the test. Now, that is a local quality metric. There are global parameters that we have to take into account, such as size, contrast, speckle edge sharpness, speckle density, distribution across the entire field of view. And as such, keeping in with the theoretical derivation, there is a global quality metric known as mean intensity gradient. Similar to SSSIG, it is a mathematical derivation of the DIC algorithm formulation process. And essentially, a higher MIG value means a better pattern, which from a layman's eye is pretty simple to understand. I know if you deform this image right here with MIG value of 212, I could probably be able to tell you exactly where it's deformed. Whereas at the bottom image, even if you're just shifting it slightly, I might not be able to tell you if it's shifted at all, right? And that's what these MIG value represents. It represents that uniqueness of features which can be tracked with DIC. Now, once we have this full field of DIC outputs, we realize that each of these subset centers is giving me displacement for that point. That is very analogous to the finite element nodal data, which means I can use DIC data within finite elements simulations to update the model so that the model starts reflecting exactly what's happening in real life. Now, there have been a handful of papers in literature where they have played with these user parameters such as step size and subset size to create the number of DIC nodes and the number of finite element nodes more. There have also been other papers where they use stereo DIC systems and they had to undersample the DIC points to match with the finite element nodes and go on from there. With that state of the art, I'm going to walk into the results and take a sip of water. If you guys are tired, I swear there are prettier pictures coming in from nature. So hang in there. All right. Whew. So results. So I'm going to move into the first identification analysis part. As I said, over my 4 years over here at Drexel, I did run quite a lot of DIC tests. This is an example over here for a senior design team called Swerve. What I'm doing is I am analyzing the conventional speckling method, right? And what I want you to note over here is this 50 to 75 centimeter length that I'm imaging, and I'm using a 5 megapixel camera system. Now for all of these, I'm going to continue using the exact same 5 megapixel camera system with the exact same lens, right? So over here, the way I'm holding and spraying with my spray paint can, I need to make sure each of these dots register at least 3 to 5 pixels per speckle. Going down one more scale, using the exact same 5 megapixel and 50 lens camera system, I have to make sure I can speckle a 10 to 25 centimeter region, ensuring that each one of these speckles are between 3 to 5 pixels per speckle. And then going further down within the micro scale, again, I've come down all the way from 50 to 75 centimeters to about 3 centimeters, where I have to improvise and I have to use airbrushes to get very fine speckles that can register at those scales. Again, we've moved further down. We start imaging within the micro scale, where we use speckling techniques such as ink toner, copper particles, or ink pattern transfers. And obviously, for all of these speckle patterns, we're running global quality metrics, we're running local quality metrics, we are analyzing the noise floor. And we realize that within the micro scale, the DIC-based error values are much lower because of the control with the ambient environmental noises, right? So that's something that's part of my lessons learned, essentially, when studying these speckle patterns. However, looking through all of these, the obvious realization is that the noise levels on the system depend on the speckle pattern along with those control parameters. So we're running analysis on all of these speckles. We run multiple quality metrics, and we try the different quality metrics that are in literature. However, we end up sticking with these theoretically derived mathematical formulations of error called the sum of subset square gradient, which is the local, as well as the mean intensity gradient, which is the global. While imaging within the microscale, we came across some work from Dr. McCarthy's team where they were using a biotemplating process to grow tobacco mosaic wires for sort of a heat transfer application. However, for me, I looked at that and we went, hey, that looks like a great speckle pattern. We are going to check out what the global quality metric is for that one. So we do an assessment, and lo and behold, this natural pattern over here gives us twice, if not thrice, the global quality metric that the conventional speckling techniques had. So then I eventually bugged Dr. McCarthy, and we had his student, Shaker, thank you, Shaker, to grow multiple viruses. But we wanted to make sure we were imaging them with the exact correct parameters. So we analyzed the imaging parameters within SAM. We found out that a low voltage with a median spot size and a high contrast gave us the best results. Finally, with the specimens that Shaker grew for us, we had viruses at different concentrations, and these are the concentrations that you see. And we compared that against a conventional speckling technique, and we realized that the viruses definitely outdoes it. And the fact that the virus grows as a scaffold, one on top of each other, and we can identify that magnification, the speckle pattern application process, the use of those patterns as speckles, enable us to attempt that multi-scale process as well. So now we have identified this high quality pattern that we cannot see, this high quality pattern that we achieved from nature. And now I want to break down what's happening, why that pattern is so good. Now, first attempts were made within the spatial domain itself using characterization tools, especially studying endpoint statistics to understand how this pattern or extract characteristics of this pattern were making it extremely good for the DIC error reduction. However, my research finally led me to believe that I should stop looking at the pattern as a 2D image, but as a 2D signal from which I can then extract frequency characteristics. And as such, those frequency characteristics could probably give me data on what's happening underneath all of this. In essence, this virus pattern is broken down into the frequency spectrum and the phase angle using these equations. And I can use these two broken down, the power spectrum and the phase angle, put them back together to get back this original image. So now I have this schematic to break things down, identify the characteristics. Next obvious step is to go through the images and see what makes it a good one, right? So I'm going through this virus pattern, which is the one that finally gave me that high quality image. I'm going to go through the different magnifications till it reaches my high MIG value, and then go down and see if I can identify any characteristics. What I start picking up is that, hey, I'm seeing this sort of like double circular event that's happening within my power spectrum, which as my MIG value further reduces, started breaking down. So there is something over there, but I want to make sure when I'm collecting this data, I have enough sample points within my grayscale value, within my image, so I can strongly represent that space. So I do a representative volume analysis where we do 128 by 128 pixels, 256 by 256. I don't really see much change over there. However, 512 by 512 definitely gives us that, that double circular spectrum, as well as 944. There is, however, not much change between 512 to 944, and 944 is computationally very expensive. So we start using the 512 by 512 pixels as our standard. I did also run a phase angle analysis across the entire field for all of these, and it looked fairly uniform within the space. With that, I want to know what's happening over here. What's going on with the power spectrum? What's going on with the phase angle? What part of it is making my spectral pattern look so amazing? So I extract the power spectrum from the virus. I create a 2D point cloud and extract the phase angle, and I merge those two together to give me this image, which leads me to believe that, hey, the image gradient information, if you remember, was inversely proportional to the error for the DIC calculation. This image gradient information comes from my power spectrum, whereas the phase angle gives me my spatial distribution and its layout, which means if I want to improve or reduce my error, I got to find out what's going on with the image gradients. So I do a power spectrum analysis. I basically break down that power spectrum and draw two lines across it. And what I'm seeing the profile is basically a noisy Gaussian. So next step, create a noisy Gaussian. I create a Gaussian, I induce some salt and pepper noise. I try and scale it because I want to see what's happening. I create an image from which I can extract the phase angle and start putting these together. What I learned then is that the image recreation process has a contrast extension. A smoother and less noisy Gaussian helps maintain the shape, which is important if we need to register those speckles properly. And finally, the spectrum generation Gaussian size analysis led us to believe that about 1/10 the size of the image helps us maintain that quality within the image itself. However, this is just the image gradient. We want to make sure our speckles are being registered confidently, which meant we had to control and create these point clouds using a pseudo random center generator where we could control the size of them as well as control the non-contact distance, because that is important when we are selecting our minimum subset size. With that, with this optimized pattern generation recipe, we are going to move into some testing and validation where we understand what the field of view pattern is. Now, before we move into numerical pattern generation, we have to realize there is a minimum subset size. We got to take into consideration the field of view. Is it large? Is it small? What's the size? And the camera assist parameters. With all of that, we want to make sure that our image has speckles that are at least 3 to 5 pixels in diameter. I'm going to create an image like that. I'm going to create a power spectrum. I'm going to put these together to give me this generated image, which then I can threshold and create my optimized pattern. Now I want to know if my optimized pattern is actually really good, because all of my theoretical derivations led me to it. I have no scientific basis or one-on-one basis to know if that actually works. So what I'm going to do is I'm going to impose a displacement, and then I'm going to throw these imposed displacement images into DIC and see what DIC gives me. And based on that error difference, I know what's actually happening. Is it actually good or not? How I'm going to impose displacement is by taking this 2D image, putting it into the FFT and shifting it, and then converting this shifted FFT signal back into 2D image. And I'm going to do this for multiple different spectral patterns. I want to analyze this one-on-one, compare it with everything else. And as you can see, I'm using images from various MIG values as well, just to assess how that goes. So once I have that, I start shifting these images from 0 to 1 pixel in steps of 0.1 pixels, which means each of those images have 10 deformed images and then the reference, all of which I'm going to throw into DIC. I'm going to get some measured value from DIC where I know what the imposed value is, and that is going to give me my displacement error, which means from there I can then calculate my systematic error. Looking at it, my generator is doing okay. It does outdo like 3 or 4, but it's still not quite there. However, when I look at my random bias error, you can see that my generated image does quite well out of everything else. And this is key within digital image correlation because it is a full field process. You're extracting full field displacement data. So outside of getting these mean average values, you want to make sure that the data that you're extracting across the entire field of view is consistent, and therefore the random bias error is quite important within DIC. However, to consolidate both these errors, we use the root mean square error method. And again, we can see that yes, the generated image system does do quite well compared to conventional speckling techniques. Given that I also do a blur analysis and a distance analysis, and all of this I do while sitting on my computer, right? So essentially, I create 2 sets of patterns. One, imagining that the camera is kept at the right spot. Another, imagining the camera is kept slightly more forward, and maybe the operator left it at the right blurring condition and at a higher blurring condition, which means these are what my patterns are going to look like. These are the ones where the camera is kept closer. These are the ones where the camera is kept further and with the increased blur. And this is what DIC is going to look at within this surface as well. What I realize is, yes, obviously the patterns where the sizes are smaller and more optimized for that generation with that spatial distribution improves my error. However, an interesting lesson that I learned out of this was increasing the blur actually improved the results. And what we realize is that's because of the back-end interpolation functions that DIC is using. It is easier to interpolate a 0.51 progression as opposed to 0 to 1 progression, right? So there's a smoother transition that's going to allow more confidence with the interpolation. And again, for all of these, we are continuously running quality metrics just to make sure we are on point with all that. So with that, we have identified, we've done the identification analysis, we've done the optimization creation, I've done the numerical testing. Now it's time to actually take all of this theoretical work and see if it actually works in real life. So we go into physical testing. The idea is simple. I'm going to do the exact same test. I'm going to select two arbitrary distances of 395 and 2000 millimeters each. I'm going to use a conventional speckling technique, which is basically spray paint. One is for fine, one is for coarse. And I'm going to create and generate optimized speckle patterns for those distances for this imaging system as well. Now, with the painting application itself, it is tiring. You do need to know, and well, you need to learn through trial and error quite a bit. And that took at least about 2 years for me to get anywhere close to being good on how to control your paint application for your given specimen. For coarse speckles, you need to make sure you're getting only the heavier droplets that's applying on the specimen. Whereas if you have a smaller field of view and your specimen is too small, you need to make sure you have finer speckles, which means I only need that mist of the black paint that is being registered on my specimen. Now I can apply the speckle patterns with the conventional method using the spray paint can. However, to convert my numerically generated on my computer optimized speckle pattern onto an actual physical test, I needed to come up with an approach. And what I thought of was, as a child, we used to get these chewing gums, well, Boomer and the other one was what I remembered, where they would give us tattoos. It was basically, you would attach them to the back of your hand, apply some water, and then when you took it off, you had a tattoo in your hand. Mad cool, right? So that was the essential idea where I said, hey, if I can get tattoo paper or water-soluble paper with an adhesive, I can print my speckle pattern, apply it on my specimen, remove the back end of the paper, and now I have my computer-generated speckle pattern on there. And why I thought that was a game-changing idea, apparently somebody came up with that 4 years ago, and there goes one more journal paper. But moving on, knowing that, okay, I can apply the speckle pattern, and now I have this system to transfer my optimized speckle pattern as well, we need to understand what the test parameters are. And this is sort of the schematic that you need to follow if you want to take any camera system for any field of view to apply these speckle patterns. You need to know what the fixed camera parameters are, the variable camera parameters. And in this case, because I'm transferring by the tattoo paper, we need to know the printer resolution. And these are the values that I have. I'm using the same 5 megapixel camera that I was doing all of my assessment with. So the equipment is all the same. When you use that, it's a 50 mm lens, and the printer I'm using has a 600 dpi. And at these two working distances, this is my minimum speckle size, which means at 0.1541 millimeters per speckle, I'm registering that speckle with the imaging system with this 5M camera at least 3 to 5 pixels per speckle. So I do an assessment, I do fine paint, I do generated paint, and generated paint, that distance was chosen because that was the smallest resolution that a printer could print. What I find out is that, hey, my generated image outdoes what's going on with the paint on the systematic error, and it's doing pretty well in the random error. However, the finer paint does outdo it slightly with the random bias error. And we assume that is because of the final paint particles that's helping with that interpolation function as well. The key, however, is we have established a threshold on both scales of generated images, the close scale and the further scale. I know that my error won't go above a certain threshold, as opposed to the conventional speckling method, where over here, this has taken me about 4 years to develop those skills to create that, right? So we've taken that variability of speckle pattern application, and therefore the variability of displacement resolution from the results that you're getting out of the equation by controlling the speckle pattern creation. And finally, we have done the testing and analysis, and at 68 slides, I have achieved objective number 1. All right, but moving on, I'm going to go a little bit faster over here. We have the applications. So my second application was, I want to try and extract multi-scale deformation information. The objective, like I said, is to extract multi-scale displacement information. The approach is then to try and utilize different spectral bands of the electromagnetic spectrum so that patterns that I apply within one spectrum does not affect the image registration for the pattern that I'm applying within the other spectrum. The idea is simple. My larger fields of view is going to be larger speckles at black on white paint. My smaller field of view is going to be smaller speckles with UV reflective paint. Further, especially if we're talking about applying this on larger structures, I'm pretty sure asset managers and building owners would not want to have black dots all over their building. As such, using these multi-spectral regimes for applying spectral patterns can allow us to assess damage while also improving the aesthetics of the building while we're doing it as well. Given that, we have to use a different camera system, which we have to validate by making sure that, hey, our dimensions and our object distance focal length requirements remain the same. Once we have that, we can create the image. Because it's a slightly larger field of view, we decided to go with a stencil, which meant we had to do a 3D printer resolution check. We found out that 1 millimeter was the smallest size through which we could nearly confidently pass speckles and apply it on specimen. To be on the safer side, we assumed our smallest speckle size should be 2 millimeters, and we created a stencil. The idea was simple. I want to take images at 2 different scales. I want to apply speckle patterns that image, ensuring it's only 3 to 5 pixels per speckle. And I don't want those speckle patterns to interfere with each other. And this is what you see. The smaller ones are at 2 millimeters. The larger ones are at 6 millimeters. The experimental setup is pretty simple. It's a cantilever beam setup. We use displacement gauges to realize the ground truth. And we calibrate our camera system by using a NIST-approved calibration block where we know the distance between these dots. So we can actually know what the millimeter to pixel resolution is once we actually image the system as well. What we find out is that, hey, the pattern that was generated for that distance outdoes the pattern that was not generated for that distance and registers well. And it also provides us with a lesser spread of noise. And with those results, we have now completed both objectives 2 and 3. So I apologize for the first objective taking longer. But moving on, with all of this data that we're collecting from the field, this multi-scale deformation information, we are getting full field displacement data at multiple nodes where we can control how many nodes we're extracting data from. We can extract that and put that within a finite element model, which the process involves collecting the actual experimental data, importing that data into a finite element simulation, and then updating the model. Now, extracting the DIC output itself requires some sort of smoothing. There's some resampling that's required if my DIC nodes don't match my FEM nodes, and some coordinate transformations are required, as you're going to see as well. I'm going to use the same test setup, the same cantilever beam. And I must note that within DIC, because it's matching these subsets by saying, hey, where is the most similar location of this neighborhood of pixels or this subset? If the cross correlation algorithm does not hit a certain threshold, DIC is simply going to say, can't find that subset, let's move on, right? So this is what fully correlated subsets look like. Whereas if your speckling is improper, if you have glare, if you have other operator concerns, you could drop subsets because of lack of correlation. And that is where having these optimal patterns that we know will confidently register within the field of view is important, especially in this step. Now, because of that, we did have some dropped subsets, and as such, we had to perform some linear interpolation to extract those points again, and then use that data for FEM update. This is the experimental setup. So we create a simple, similar cantilever beam. It's an aluminum beam. It's a C-beam essentially with a Young's modulus of 68.9 GPa. We loaded as we loaded in the experiment at 25 pounds, 50 pounds, and 75 pounds. And because in DIC, when we're doing testing in the real conditions, our camera was not perfectly horizontal. It was slightly more tilted. So we had to play with our DIC system and realign the coordinate systems and interpolate the data within the finite element nodes and the DIC nodes. So there is some work that's involved over there, but this is more of a proof of concept to show that, hey, we can actually achieve, instead of singular points by using contact sensors, by non-contact, I can achieve an array of points to extract displacement, which I can then use within FEM. Now, for that, we create the model. And what we realize is, say, if my beam, when I load it with 25 pounds, goes down 1 inch, my simulation tells me if it has to go down 1 inch, I actually have to load it by 40 pounds, which means in reality, my structure is a lot weaker than what I believe the simulation that I could check would provide, right? And that is where this model updating concept could be very useful, especially for asset managers, where we can properly replicate whatever the the damages within the structure, the defects, the lack of boundary conditions within the actual structure is with the finite element model, where we can then push the finite element model to identify critical parts. Again, doing this in a very crude way, my idea is simple. I'm going to compare what's happening in real life with the DIC, compare what my simulation is giving me. That displacement is not the same. I'm going to update model parameters, and over here, I'm just updating the Young's modulus and making it a weaker material so that it can identify similarly to the weaker material in real life. Update that, and then I'm going to check what the response is at 50 pounds. And I see that it is not quite the same. So I'm going to do the same process. I'm going to update what's going on with the model. I change the model parameters. So I again, make the material a little bit weaker in the simulation. And I compare what's happening. I try and predict what's going to happen within 75 pounds. So what's eventually ended up was my Young's modulus that started out at 68.9 GPa finally went on to 58.25 GPa, right? However, I was able to predict what was going to happen at 75 pounds accurately with the simulation without actually using the 75-pound data in my model updating process. And as such, this becomes hugely useful for asset managers to extract this full field displacement data, apply to a model so we can push the model to failure while knowing what's going to happen with the structure as well. And with that, we've done the identification analysis, optimization creation, testing validation, and the applications, and objective 4 is achieved. All right, and finally, I'm going to move into my conclusions. So with this dissertation, I was aiming to extract quantifiable multi-scale deformation information by using photogrammetric methods. I did this by developing a method to generate optimized scalable patterns that improve the displacement resolution as well as reduce the errors. I was able to achieve a multi-scale deformation information by using a multispectral approach to extract this far and near field spectral deformations. I validated the pattern transfer, the quality, the sizing for these tests, and then provided a multi-scale diagnostic tool which could be useful for a goal of, say, structural health monitoring. And with that, my innovations and contributions to the field is to help improve significantly the results that can be extracted from DIC by primarily not just removing the variability of the human factor, but also establishing that error threshold by controlling the spectral patterns that we are actually tracking. This is done by a process which takes into consideration the testing parameters, so your camera image equipment, the image gradient, as well as the spatial resolutions. I propose the use of alternative methods to transfer this created pattern, such as the WTP or the stencil use onto a specimen. I developed a methodology to create spectral patterns for 2 separate scales of multi-scale deformation assessment, and finally developed a methodology to extract full field 3-dimensional data towards a finite element simulation for model updating. Some of the future work that we actually are trying currently with one of the senior design teams in our in MEM and ECE is we're trying to get live transmission of data out of the DIC as we're running the test so that strain data can then trigger other systems. And now this is running better because we can confidently register those speckles which are being tracked across the entire field of view, which we had a problem with because of the random speckling techniques that was conventionally used. Further, if we have these imaging technologies on like UAVs or drones, and this is some of the initial work that my friend Andrew Allenberg, also my lab mate, and Dr. Bartoli and Dr. Constance has done before, is to perform remote sensing for structural health monitoring, where we can assess these non-destructive tests with optical metrology, and then provide that information to the asset managers to help perform maintenance and diagnostics better. With that, these are my journal publications, since I've actually started this, my research with this group. These are my conference publications as well. We have a patent application that's under review for the same spectral pattern optimization methodology, as well as the multi-scale multispectral aspect of it. These are some of the references that I've used in my thesis. And with that, I would like to thank Dr. Consos for hanging on to me over these 4 years, 2 months. I would like to thank my committee members, Dr. Lau, Dr. Chang, Dr. Bartoli, and Dr. McCarthy, and especially my entire theoretical applied mechanics group for all the constant support, the friendships, the coffee runs, everything over the last few years. I would like to thank all of you for taking the hour off, hopefully just an hour, for listening to me. And with that, I will take questions. Thank you.
Thank you, Melvin. Thank you. Thank you. 52 minutes, that was a lot of stuff to cover.
Yes.
At this point, and to respect people's time, do we have any questions from the audience before the committee excuses itself for some time with the candidate?
Antonio, I have one comment and question. I think these are mind-boggling collections of pictures and images and data. Yes. So I'm just wondering how Melvin went through all these images and was able to come up with a valid conclusion through experimentation. Where did he save and store this data?
So Melvin, you can comment on that.
Well, to store the data, our research group has a server that's allocated for us. And Dr. Consul has been kind enough to give me multiple 2 TB hard disks that I can run around with.
Wow.
Yeah.
But you also use online references, right? You have some standardized pictures that we have in that community, and you use that for training as well, right?
Yeah. So some of the images that I use, especially with, I don't know if you guys can still see my screen.
Yes.
If you can. So these DIC-C images are part of the Society of Experimental Mechanics, where they release linearly shifted images as a standardization. So researchers who create their own DIC algorithms can use that to find what the errors are. So there are different image sources for DIC available online as well.
Okay. Thank you. Great presentation.
Thank you, Jay.
Any further questions from our audience?
I do. I just wanted to say, excellent work, Melvin. You really did a great job.
Thank you.
And I do have one question about the interpolation methods. So you
Sure.
had mentioned that there's like subpixel resolution. Did you do any experiments with like basically different orders of the interpolation? So like third or fifth or anything like that?
So I did do bilinear, bicubic interpolation. Then I did a numerical binning interpolation, and I followed the numerical binning interpolation because I assumed, and let me explain what the numerical binning interpolation was. I took a high resolution image, I shifted that by 1 pixel, and then I binned that image down by 10, right? So I should essentially get a 0.1 shift. And I did this because one of the premier people within the DIC field do that. But however, the more papers I kept reading, the more they kept recommending that we should use the frequency-based linear shifting, and which is why I just went back with the standard. But the results are the same, whether I use the bicubic, the bilinear, or the frequency-based as well.
Very cool. Good work.
Thanks, Andrew.
And any other question, the last question perhaps from the audience before we exit?
Melvin, one simple question for you.
Sure.
First of all, nice presentation for me because I know nothing about DIC.
Thank you.
And it was wonderful working with you. All right, so just one thing, like when I was looking at your data, like I saw like sometimes you choose pixel size of 128, sometimes pixel number subset, and sometimes the subset is like 2-3 pixels, something like this. And I don't actually understand whether there is any relation, like how you're choosing a subset, or you're following any rules with the MIG
Yes.
or anything for feature extraction. Sorry.
Yeah, no, absolutely. I mean, that's an accurate, that's a very good question. That's one of the first user controls that we learn as a DIC user, where we want to make sure our subsets are large enough to have at least 3 to 5 speckles, right?
Okay.
And especially if it's a randomized applied speckle pattern, there are chances that you have blobs at parts of your image, which means if your subset is too small, you won't identify damage within that. So we have to like increase or change our subset size to pick those up as well. So which is why you're seeing that variability. But ideally with this method that I have developed, where we have established what the size of the speckles will be within the field of view, we can use a more standardized subset. Right now, this is not a concern within the DIC community because DIC is just getting picked up quite a bit. But soon when we have more and more users, they're going to start realizing, hey, we got to train our operator outside of being a PhD student or a researcher as an actual operator to use DIC. But this has to be a quick, standardized, reliable testing process.
Great, thanks.
Thank you, Shekhar. If there is no other really burning question, if you have, please let me know. I'd like to thank you. Yes, Amir.
Good. Well, Melvin, nice presentation. I really enjoyed your presentation.
Thank you.
Question regarding the place that you compare the nature-inspired virus pattern with copper base. I think it was slide number 48.
Yes.
49, something like that. Yes.
Over here.
Then you show that, okay, so you do have that number MIG values, 154, and you compare it with copper speckling, and you say that, okay, virus is much better, virus-based pattern, but how you make sure that this comparison is correct? Because virus is going to be, you're going to have many of them smaller size, and the way that it's scattered on the surface is going to be like very like so you have more dots there, right?
Yes.
So how can you say that this is a real comparison, and how what are your thoughts on that?
So the copper speckles only allow us, because of their size requirements, only allow us a certain field of view within which we can accurately use copper particles as speckles, right? However, with the virus, we are able to do that multi-scalability. But what we did was, when we ran this assessment, when I pulled out these numbers, we were assessing the copper spread and the wire spread at that same magnification for the same field of view. So we had that one-on-one correspondence as well. And when we did that one-on-one,
let's say the cell size or the particle size, were they comparable, like copper and cell? So no, then, if that is the case, how you could say that this comparison is correct, because you're showing that 3 times more virus spectrum will give you more resolution, but it's actually like you're putting more particles there, smaller particles there, and
yes, and that's what's essential to improve the DIC pattern quality. And having that gradient information, which then relates back to this error value, is what improves the quality of the DIC, which should have been like understood to us, where this actually makes sense, having more particles. And that's sort of what I show with the MIG value as well, saying that, hey, if my particle size goes quite low, my quality increases. However, we also do have spatial limitations, right? Because when I'm imaging with the imaging system, if I need to confidently register a speckle, it has to be at least 3 to 5 pixels. Because if not, my best way to get the highest amount of image gradient is to have a checkerboard with 1 black, 1 white, 1 black, 1 white, 1 black, 1 white. That's going to improve my gradient drastically. But I can't use that as a DIC spectral pattern because I have these imaging limitations, which I showed in this slide right here.
In the
that kind of answers the question.
I would like to make a final call for people to perhaps show their videos so we can take a picture of the whole thing.
Yes, please.
Realize this. If you don't mind to show your beautiful...
You guys could all turn on your videos just so...
I will collect a picture right now. If you're ready. Reza, Masood, you're not there? You don't want to be there? We'll have you in. Okay, maybe, okay. So thank you, Masood. All right, ready? Reza? Reza fell asleep. 1, 2, 3, take it. Got it. Right. Thank you. Thank you very much. Thank you very much. So
thank you.
I just want to get the second page as well. I just got only 1 page.
Okay.
Sorry. If everybody could turn on their cameras again, and I will get the second page as well. All right, perfect. It is so nice to see all of your faces, guys. Thanks a lot for attending.
Thank you.
Great.
Thanks.
All the best to you.
Thank you.
Good luck, Melvin.
Thanks a lot, guys.
Good work.
Everybody, thank
Bye.
Melvin.
Good job, Melvin.
you. Please.
Good job, Melvin.
Thank you.
Good luck.
Hey, wish me luck. Wish me luck.
Great job.
Good luck.
Good job, Melvin.
Good luck.
Melvin.
Great job.
Man.
Thank you. Thank you.
Good luck.
Perfect presentation. Good luck.
Thank you.
Good job.
See you, Andrew.
Bye, Andrew.
Hey.
David.
Hey, good uncle. See ya.
Parents, don't go away.
Bye, mom. Bye, dad.
I can put them in the waiting room if you want to.
Bye.
All right. Again, if you're not part of the committee, Brinda, Pratik, Dr. Teresa, let us know. So, Melvin, are you okay? You want to take 2 minutes perhaps to drink some water? I know we'll be behind.
I think is it my net or your net that's
Could be both. It's a combination of things. So, okay.
Okay, I see people leaving.
Yeah. So the committee members, how are you guys?
Good.
Good. It is what it is now. So do you want to start immediately? Melvin, you're fine. You want to continue? You okay?
I'm just going to like take a sip of water.
Perfect. Yeah. So BC, you're the chair. Please follow your own method of the committee.
Yeah, I think I can continue. Yeah, it's just you can represent me.
I picked up the role because of your delay, and obviously,
yeah.
just for your Zoom issues, it happens everywhere. Okay, so see, all the committees are here. Yeah, everybody's here. So anybody, feel free to ask any question. Melvin is here for this call, so let's make sure he gets a lesson. Yes,
Dr. Patel.
Hi. Hey, let me get. I got a very good presentation, Melvin, and I got probably a couple of questions. Only a couple of questions, and so the parameter that you look at to understand if your pattern is good is the MIG. You often refer to MIG, or are there other parameters that you're looking at?
So there are multiple other parameters. Hold on, I'm not sharing my screen. My bad.
No. You don't have to share the screen. I'm just.
Yes, I do look at multiple parameters. So I look at a local quality metric. Remember from the denominator value, which is called sum square intensity gradient, and that has been highly recommended in literature as well because it is based on the theoretical formulation of DIC, right? And MIG is sort of just an extension of that within large value. But there are other metrics. There are entropy values. There are grayscale local co-occurrence matrices, there are mean subset fluctuations. And I do assess all of these. And I see that the trend is the same. Like, a good speckle pattern shows up quite well with MIG-SIG, which has almost a linear proportional trend with the other ones, which is why, because there is this dependence on the formulation, the DIC algorithm formulation for these two quality metrics, we just use them.
Okay. And my question is, so you're developing a new pattern. Is there a risk that the quality of a pattern deteriorates during the test just because you're coming up with a new idea, new material, whatever, and consequently you should look at this metric not just only at the beginning when you have the specimen that is undeformed, theoretically undeformed, but also at a stage where you want to make sure that your deformation information is accurate. So in other words, just to give you an example, if I use a regular strain gauge, the fluctuation could be 1 microstrain.
Right.
Then I apply a load, I read 500 microstrain, but the fluctuation is still 1 microstrain.
Right.
Did you, through your experience in testing your new pattern, make this quality measurement at both the undeformed configuration and at a configuration where you have significant load, such that perhaps the noise level or whatever metric you're using to evaluate the quality of your pattern might have changed? Did you do this kind of comparison?
No, primarily because the way DIC is constructed, the algorithm itself is based on the continuum mechanics small scale deformation profiles. So we are not expecting that much change. And like I said, the fundamental assumption with DIC is the neighborhood of points is going to remain that neighborhood of points. However, there is another process called a step-by-step DIC. Say if I take 4 images, right now I'm just comparing all 4 images to my first one. Instead, what I can do is compare my second to my first, third to my second, fourth to my third. So I'm establishing new subsets, which I can then track and then accumulate them, so I won't have that speckle pattern deterioration. From a practical perspective, as somebody who's had to do a lot of like spray painting, they say that you should speckle your pattern and use it within 4 hours, because the paint will cure in 4 hours. And now you are looking at the deformation profile of not just the material underneath, but the additional deformation of the paint as well. So there are a lot of practical applications that you need to look into, especially as a DIC user. But the versatility and how easy it is, like I don't need to glue, I don't need to epoxy a strain gauge onto it. I can spray something on and stick a camera and I have full field displacement. That versatility is still being kicked in within the DIC community. And that's where the excitement is. And that's
so following up on what you said, that the paint is basically curing, and consequently, ideally, you should do the test within a certain time frame. That potentially could affect, for a really long duration test, the quality of your measurement. So depending on the application, you have to use different products, and that's understandable.
Yes, depending on the kind of speckle pattern application method, right? So when I say paint is curing, I say that because I'm applying a base layer of white paint. So it's a flat layer, and then on top of that, I'm applying black. But if the material is already white, I'm just putting black dots. Now I'm fine, because the underlying deformation is the material itself.
Yeah.
Right. So these black dots are an intimate carrier of the surface deformation profile of the material, and not this base white layer.
Okay. No, the other. So as I mentioned, I got 2 primary questions. Sure. The other one is on slide 82. If you can take a look at that one.
Yes. Yes, I have it. This is the model updating slide.
Yeah, and basically over there, I was wondering, can you explain again why you get young modulus that is so low for the aluminum beam? I mean, that is not a standard ASTM standard quality control material, but 58 gigapascal is really low for.
Absolutely. So our idea over here was just to do proof of concept. We had done the test for the multiscale multispectral, and we were wondering we could actually use this data to pull it back into the model and update it. And I'm not very strong on the simulation side. I'm more of an experimental guy. So using some of the leverage expertise from my team, I just wanted to see, can I do some sort of crude way of model updating?
Yeah.
And for my crude way, I created an elastic model where it was just Young's modulus and the material. And I saw that in real life, my material was actually more flexible than the simulation. So I just made the simulation more flexible as well. That is as much of the thought process that went into that.
Yeah, so I suspect that possibly the boundary conditions
are
not fixed, so they are reflecting a lot of flexibility of your beam. That's
Absolutely. That's why I did as well, but I didn't have DIC data from the boundary conditions to actually validate that.
Okay. I'm down for now.
Thank you, Ivan. Committee members.
I have a question. Great work, as always. I've seen you talk a billion times at this point. I forget even what is new in this compared to what was last time, but great work. My question is, we've talked a little bit about this in the past. Because your work is in a lot of ways, you could refer to what you've done as sort of proof of concept, right? You have this idea of using these patterns, and you've proven sort of these little components that you can stack 2 patterns on top of each other, that you can find optimization, all the sciencey stuff that I'm not quoting correctly, but you looked into like what an optimal pattern is, and you played around with creating it. But one of the big sexy things you were selling is this idea of using it in the field for non-destructive evaluation to stop bridges collapsing and applying it in the field, which is really challenging. And I know that, and this isn't your job as a PhD student, but to have solved these problems. But there's got to be some major technological hurdles between now and actually using that for that purpose, where you could sort of apply a pattern at some early stage and then leave it there for months and years and come back and check it and use this technique, right? That's the idea. You lay this pattern down early and it has to live. So what do you think the real technological challenges, not necessarily your work, but the side challenges, the technologies that need to be invented for this to be implemented in that way, what are they, and are they realistically overcomable?
Sure. So I did sort of like delve into the process that we might have to use, because before the COVID lockdown, I was in conversation with Dr. Bartoli about potentially using this on like a larger bridge kind of structure. And the concerns with that is, first of all, we have the camera technology where if we want to get a larger field of view within the same space, we are going to have to use a wider lens, which is a fisheye lens, right? And to calibrate that, bring that back is one. Secondly, we have to move, depending on the size of the bridge, is to stitch all of these images together. Now, the stitching algorithm is not as accurate as the DIC precision, which means we could have some errors just because of the stitching process. Well, and then thirdly, the confident application of these speckles and seeing how long are they actually going to last. Like I can apply it today and come tomorrow, I know it's going to last. But if it's raining for a week and I come a month later, is my speckle that I applied going to be exactly where it is? Is underlying corrosion going to affect the way I'm looking at things? And those are sort of like the hurdles that I was imagining. Are
there applications of this that really are in the days and weeks scales? I've always viewed this as years, decades sort of scale. So I'm not to be crass about it, but can you put anything down on a steel bridge that's going to be there decades later?
So if you're looking at, say if you know there's a crack zone, right? Like, you know, a gusset plate is kind of weak. You can apply a pattern on it and come back a month later, especially if it's something that's on the underhang of it. You can come back and assess it, and you can see what that deformation profile is. If you want to look at the entire structure, there are papers where they use DIC, but essentially they could have just used point trackers. They put magnetic plates at like each pillar, and they basically use DIC to track how those move. So those are things we can do within the next month or weeks.
Well, that was sort of what I was getting at. It feels like I'm questioning whether or not what you've done is optimize this to this extreme level that in the lab you're finding these perfect ways for this to operate. And then you might get out into the real world and you're so handcuffed by the reality of the situation that, you know what I mean? You're sort of in this dead zone of fundamental and applied, where when you want to be fundamental, you can be fundamental. When you want to be applied, you can be applied.
Sure.
So anyway, that was one issue. So this sort of targeted use, you're saying you could like identify a problem and come back and speckle it as for like an area you need to check up later.
Yep.
So in the lab setting, does this have a deep usage with the in the lab where you can? Do you really need multi-scale structures in the lab where you have 3 different sets of dots, or could you just replace that with 3 different cameras? Is that really if the other application is to use this in a more controlled setting, does this technology, this idea of having nested speckle patterns at different scales and different wavelengths and all the crazy stuff you were looking at, does that really gain you that much in the lab that you couldn't do with just hardware, other type of hardware, or, you know, one really great speckle size and a really fantastic camera that looks at really small scales? Do you need the multi-scale stuff in the lab?
Right. So the usage of DIC is mostly tailored towards what kind of damage we are expecting. So if you're looking like an isotropic elastic material, say I'm just pulling an aluminum dog bone, I can use just one scale of DIC and I can find that elongation neck. But however, if I'm using like the carbon fiber IM 87752 composite material, now I'm going to have these little crack functions that are kicking in, where I want to be able to study, hey, are those cracks leading immediately to delamination? Is that fiber breakage? And that's when you would really like, as a researcher, to be able to go closer by and get that information as well. Now, as opposed to being just a straight edge or a specimen with no cuts, especially if you're doing like an open hole test, this microscale pattern within closer to that pre-damaged location would definitely help us acquire a lot more image. Now, we've done DIC with the open hole test as well, albeit, so we did 2 cameras at an open hole test at a single scale. And then we placed a camera on the side of it because we wanted to understand delamination as well. And we applied a DIC pattern on the side. So we have tried different aspects, just not within that same region as well. But there would be requirements, as I said, depending on what kind of testing or damage we're expecting from the test.
Okay. Have you ever thought about, I'll finish here, but have you ever thought about using this specifically for fatigue testing, like using this in a suite of I forget what the right word is, but like a standardized testing package where you put in a sample. I know in heat transfer, it's very different. We're not really looking at mechanical stuff, but people always want to know 30-year lifetime of the thing we're designing, and it's possible to do accelerated testing. Is there a way to use this in accelerated materials testing?
Yeah, and we have done quite a bit of that. It included me having to Python code into the software, picking up just peaks, because DIC is the exposure time, it depends on how much blur you're getting. The amount of blur you're getting depends on the displacement resolution that you're extracting from DIC, which means if I'm doing a long-term fatigue or I'm doing high speed rate fatigue, I need to be able to take images at exactly those same load values so I can consistently pick this up. So we have used DIC by coding in the load value that the system is at and triggering DIC to take images at that same time. So we have consistency for fatigue life cycle. We've done this for aluminum, for the carbon fiber test. I think M&A brought in some sort of polymer material. They just call me, if they want to use DIC, they call me. I'm the power user of DIC within the lab. So,
but it might be interesting. I mean, it's like I'll finish right now. But it might be interesting to use this for like larger than coupon level, but like part level sort of analysis, because in fatigue testing or these accelerated lifetime testings, you don't know how it's going to fail. You don't know what you're looking for. So it could be a place where the multi-scale thing is really important because you want to stand really far back and look at the whole thing, but you want to zoom in on corners and, rather than, just look at a corner, it's going to fail where dog bone's going to fail. But if you have a more complicated part, I don't know. I was just sort of thinking that. All right, great work, man. I'll pass it off to somebody else. It's nice to see everybody. Probably one of the biggest turnouts to a defense because it's all on Zoom.
Yeah. How many people did we get?
53 tops. It fluctuated. But 53.
All right. I'll take it. I'll take it. I'm glad I didn't have to buy 53 samosas, but it's good.
Yeah.
Food.
I can send you my home address.
That's
Melvin.
true.
Send me your home address.
You only need 6 emotions.
I would like this address. It should be noted.
Well, Melvin,
Dr. Lau, I'm sorry.
a great presentation and good work.
Thank
I would
you.
say that you have made a very concise and compressed presentation. Your presentation was about 52 minutes.
That's all Dr. Consos. If not
Right.
for him, I would have about 55.
You said that you have spent more than 4 years doing this work, right?
Yes, sir.
Each year is 52 weeks. So basically, every minute that you present represents 4 weeks of work, right? At least. So it is pretty concise.
I did
Now-
go on vacation in between, but it's all right.
Okay. Now, of course, then you can say your work is not continuous. So sometimes a lot more productivity, sometimes no productivity.
Absolutely.
So that brings me to the one of the questions. In the method that you use, you need to use interpolation. And we know interpolation has underlying the assumption that things has to be smooth,
Right.
varying. Now, if you put the markings on a bridge, we know the bridge is not made of one monolithic material like aluminum.
Mm-hmm.
Some part is steel, some part is concrete, some part is wood, some part is damaged material.
Right.
So even if the overall force is uniform, because materials are not uniform, we can expect the strength field could be not uniform. And sometimes there would be sharp changes from one point to the other.
Mm-hmm.
So how does the theory account for such drastic change. And at some point, if there is damage, like a crack, there will be sudden discontinuity also, right?
Yes.
If we still use the theory that it is continuous, then the results that we get from interpolation and continuous result may not very accurately represent the conditions of the bridge. How can we improve on this?
Okay. Can I confirm, when you're talking about interpolation, are you talking about when I used interpolation for the model updating, or are you talking about the built-in interpolation within the DIC algorithm?
Well, basically, you just have a bunch of dots, a bunch of points, and how these points move. From the movement of these points, you fill in the gap in between what is the stress, what is the strain. And from that, you need to have some, I assume you are using continuous assumption, continuum mechanics, right?
Yes.
But
so
a bridge is not continuous.
It is not, but we have to take the material away from the digital image that we are actually using. Because as far as the image is concerned, it is a spread of grayscale values. It doesn't know anything else. And what it is tracking is a subset of the grayscale values we're going to interpolate. Now, if my subset gets too wide because of, say, I have two different materials, my underlying material goes further away. Now, my image is going to look at, hey, I have no grayscale over here, but I have the registered grayscale over there. So it's not the same subset. I can't register it. It's gone. The continuity is canceled over there. So with DIC's fundamental algorithm does not care about what the material is. It cares about having a digital form of an image. And the interpolation is just put on the grayscale value. How we analyze the data that we get from DIC would then be dependent on the kind of material that's underneath. And that would be essential when we are using this DIC data into like a model updating. I used a very simple system, right? But if you have a complex structure as what you're recommending right now, we have to be careful about how we are assessing that equivalence within DIC and the model.
Yeah, thank you. So that answer brings the second questions. You had mentioned that you had a method to do multi-scale observation and analysis. So as engineers, I would like to ask, there are many people say the word multi-scale. So what scales are you actually mentioning? From what macro scale to what minimal scale? How many order of difference in length?
So my proof of concept, I did a scale of 2 meters away from the object to a scale of 6 meters away from the object. But however, because now I can control the size of the speckle that I'm actually applying, and as long as I know what the megapixel count of my camera is and the lens are, I can create a speckle for any scale.
So translate
the versatility of
now. So translate it to a bridge.
Right.
So translate it to marking on a bridge, for example. So how many order of length? Let's say how many feet, from how many feet to how many micro scale are you talking about?
So we could probably do centimeter registrations, especially on like critical locations, to meters further away. And if we want to go further away, if it's a longer bridge, we can use point trackers on the functions as well. And we can build all these in. Obviously, for micro level testing, I'm going to need to stick a optical microscope on the bridge to assess what's going on. But we could also do that as well.
Okay, so basically you say you could have the scale of 3 feet down to the scale of less than an inch square.
Yes,
right?
Absolutely.
Okay, so now it is fair to assume in a material on a bridge or some infrastructure in the square of 3 feet times 3 feet, probably the material may not be monolithic material. Probably there could be a crack, and probably also over time damage will evolve, and when there is damage, the location of the damage could be different. So somehow we have to to put in those discontinuity maybe in the next evolution of your theory.
Yes. And so let me just confirm, and I believe this I've also realized is one of the potential gaps within DIC. Let me confirm if this is your question, that as given that we have applied a spectral pattern over time, the structure is that within the same reference zone. Is that what your question is?
Mm-hmm. I did not hear your somehow for some part of your answer. I did not hear any voice, so I'm not quite sure what was your response.
I can repeat that again. I was just clarifying the question to find out if what you were asking was, hey, over time with the structure deforming, how can I make sure that I am getting it within the same region?
Yes.
Is that? Yes. So there was a paper where what they did was they basically put two fixed point markers at two different sides, and in the middle of the structure there was a crack, and they used that point marker as the reference point, and everything else that moved around it moved around it. But this was the reference that was fixed, that the image was fixed to, then compared again. They did the same thing on the left hand side because they wanted to see how the cracks were moving on either way. But yes, that is a problem because we need that image to remain technically within the same field of view. And if that field of view changes, we got to realign the field of view to make sure what's happening.
Okay.
Now that could be a problem when you're assessing displacements. However, when we are assessing strains, we can work around that within the DIC software.
Okay, I have one more question.
Absolutely.
Let's do a thought experiment. Suppose you go to a grocery store and you buy 2 watermelons.
Okay.
They are more or less the same size. You bring the 2 watermelons home, and on each of the watermelon, the surface you put in the speckles.
Yes.
Now, every day you take your camera and see what happens.
Yeah.
And for a period of 2 weeks, you don't observe any difference between the two watermelon speckles.
Right.
But in fact, one of the watermelon inside is every day is rotting. And one of them, after 7 days, no good at all. If you touch it, it may crumble. But the other one is perfectly okay. But the speckle on their surface doesn't change at all.
Yes.
So how are you going to convince people that if you put markings on a bridge and you can actually very reliably tell people that what is the condition of the bridge?
All right.
Over time.
So
the
first thing
is tricky, but there is logic. Please follow the logic, please.
So first of all, I want to say DIC, the way the 2D DIC, stereo DIC, can only be used to track surface changes. So anything that's happening within the watermelon, I cannot find out. There are uses of digital volume correlation where they can track the seeds within the watermelon to identify how it's moving. Now, given that, we also want to say that, hey, instead of using DIC with regular cameras, we could use IR cameras that could potentially pick up subsurface delaminations, which we could then identify what's happening underneath the surface. Or we can really hope that what's happening underneath the surface is going to affect the surface profile and thereby pick it up with just regular scale DIC. So that would be my two options to identify subsurface damage.
Maybe what if you apply a load on the 2 watermelons?
Hey, that depends on whoever's applying the load. If you apply the load, you're going to see those surface deformations kick in for something that is weak on the inside, as opposed to something that's sturdy on the inside. And then I can use just regular DIC for that.
Yeah, but they have to do the same thing on a bridge. Without knowing the load, Melvin, measuring a deformation is not really valuable.
Yes.
So you need to correlate the load to the deformation, and then at the point you can You can see your bridge as a spring, you can see your watermelon as a spring, and you can estimate the stiffness of the spring.
Absolutely. I am trying to improve the data that you get to do that assessment.
Yeah, I understand. But don't forget that you're an engineer. You're not just a specialist to measure.
Absolutely. I've been talking with Dr. Consos about doing some funky tests, but you know.
No. I mean, you're aware of, but don't confine yourself in an expert of DAC. You know, despite the fact that DAC is a great tool, but you're an engineer that is an expert of DAC.
If I may comment here, when Ivan and I started working in this field, we both realized that people don't try to improve the method much because the method is so rich in information they don't care, right? But Ivan and Professor Lau are perfectly correct in the sense that, as we discussed several times, Melvin, what you see on the surface is the surface projection of a three-dimensional volume state, right? So you can't decorrelate the volume response, as Professor Lau and Professor Melvin said.
Yeah.
It's the projection. When I think of a crack growing in a specimen, the crack inside the specimen will definitely weaken what you see or change what you see on the surface, right? So there is possibility to get what Professor Lau said. So just making sure.
Do you mind if I just step away for 1 second while I fill some water?
Sure.
That's a good problem, Alan. And I think you asked Ivan's question for the modality on a different perspective.
Now, I think that you have given a very good answer. Next time if people ask question like that, then you can say that the condition of infrastructure is a holistic problem. So it needs a holistic multi-module method to determine the state. So the DIC, what you are working on, is a very important module of this multi-module method. And if you are an engineer, then you will continue to develop the other modules. You know, for the watermelon, people buy watermelon, they just don't want to look at what is happening on the outside, right? They slightly knock at the watermelon, just hear the reflection of the sun, then they can tell something from the inside. So you could have a multi-module method to determine the current health of that infrastructure. DIC is a very important module, and then simultaneously, maybe intermittently over time, you can have other modules.
That's right. Thank you.
Thank you.
Okay, probably I'm the last one.
Yeah.
Okay, I'll make it short. Yeah. So now first of all, I think the presentation is great, and the problem considered is very important. Yeah, but it's not an easy one. Yeah, so although basically it's kind of a comparison of like two images, but you know, so we how to determine it's good or it's bad, it's really challenging. Yeah. So basically, I think you use a marker, you know, but this marker, it's going to fade away as time goes by, right? And you also, of course, you also compare to the kind of the original image and the new image, and to see what's the difference between them. Okay. But now all this, I think, are like related to computation, algorithm, and so on. Yeah. But I have a question about this implementation. Now, how are you going to implement it? So you're going to go there, take a picture, and send a picture back to the lab, and to do computation to determine what next step needs to be done, or you're going to do it in real time.
Are you talking about the implementation of applying the speckle patterns?
Yeah.
Well, even before we go out into the field, if I know what the area that I need to look at is, and I know what camera I'm going to be using, I can prepare from the lab and come with the material to the field. As long as I know if I'm going to be looking at a 5-foot by 5-foot wall, or the other one, I can prepare for that.
I think the question has to do with processing mostly. Are you going to be processing on the field or near time on the field, or you have to store images, go back to the lab, or send them to the lab? Some will do the processing, some computer, then send you some information back, and you're able to continue the test or stop a test until something else is validated.
No, we can do it. We can do it real time. There's no reason to not be able to do the quality analysis real time. And right now, the DIC commercial software, the latest release of Aramis, does allow you a real-time pattern quality. But if you want to be able to apply the Speckle pattern, you need to know beforehand the region that you're looking at and the image acquisition system that you're going to be using. With that, you can come prepared to the field. And right now in my lab, we tend to use about 3 to 4 different scales of distance with the same 5-megapixel camera. So I have pre-printed sheets that my lab mates can just go cut up, use the WTP, apply it, and get this confident resolution. So if we know what the distance is and the camera system, we can walk into the field with this sheets of paper that we can use. So it's a ready, set, go plan if we have that information.
Yeah, I think that the distance is important, but the angle is also important. So you may have, it's very difficult to have a two picture, kind of an identical angle, identical distance. So the picture, I think, even they are identical, but you take a picture 2 different times, they may not match well.
True. So there are systems that come locked in, where the cameras are prefixed to look at the same spot, and they're calibrated for a certain region. So you can just go into the field and use it if that's what you're asking. Or are you asking about taking one image now and taking one image a month later?
I need to clarify here. In your implementation, Melvin, you can have both 2D and 3D pictures. 2D meaning from a single camera, or 3D from a stereoscopic pair. I think perhaps Professor Chan could clarify if he's referring to a single camera use where the camera angle is important, or the stereoscopic use of the DIC, which is what you are mostly referring to. Essentially, the camera angle is very important, but then the actual camera position is not relevant, because once you have the calibrated space, perhaps that doesn't make sense. So maybe you can clarify what perhaps condition is more important for Professor Chan's question.
Okay. So with you, we can use multiple cameras. We just need to use at least one camera. Now, the thing is, if we're using 2D DIC, that's known as the use with just one camera. The assumption then is that the specimen that we're looking at is parallel to the surface of the sensor. So there's that one-to-one relationship. Now, if I'm using 2 cameras, I'm going to lock them into place and make sure that their center optical rays meet a certain spot. And then I'm going to calibrate a certain field of calibrated. Anything that comes into this region of volume that I've calibrated can be used for DIC.
Yeah, talking about 2 camera, I think the camera, even the same picture, you use 2 camera, you're going to have, so if you want to compose to see the kind of a global view of a camera of a picture, then you need to know the so-called pose, the pose of each.
Cutting out for me, or
yeah. But anyway, I think that's this kind of practical issue is something for other people to consider. But I think your contribution in the lab it's significant. Yeah. So I think we my question just stopped here. Yeah.
Okay.
Melvin, if you don't mind, stay where you are. I'm gonna move you in the virtual waiting room, and when I call you back, make sure your computer is on so you can actually do this. Okay? So I'm gonna be withdraw co-host permission, and then I'm gonna be sending you to the waiting room. Okay? Okay, Melvin?
Yep.
You good? Okay. Don't go too far.
Yep. I'm right here.